Alright, what I'm going to do in this video is just kind of quickly go over these notes on section 1.8 on infinite limits and limits at infinity. And actually, for the most part, I'm just going to talk about this limits at infinity part because we've really already talked about infinite limits. Infinite limits are an occasion where you have a limit that's equal to either infinity or negative infinity. So we're talking about the limit as x goes to a, f of x equals plus or minus infinity. And we know that really what that means is that we have a vertical asymptote. Okay. We've already talked about that, so I'm not going to spend a whole lot of time on that. What we're going to mostly be talking about is this stuff over here, limits at infinity, and that's when I have a limit as x goes to positive or negative infinity of some function. So as I go out towards infinity, what's happening to that function? Right. So the only thing I really want to hit clearly, is this justification of the existence of a vertical asymptote using limits. And the way that we do that, we've done this already, is we can say f of x has a vertical asymptote at x equals a if the limit as x approaches a on the negative side of f of x equals plus or minus infinity, or the limit as x approaches a from the positive side of f of x equals plus or minus infinity. We've done those problems, so I'm not going to really worry about that right now. I want to focus on these horizontal asymptotes. Okay, so horizontal asymptotes occur when we're talking about x going out towards negative infinity or positive infinity. What this really means is something we've done you've done in like pre-calculus classes and even algebra 2, is really we're just talking about the end behavior of the function. The end behavior is either going to negative infinity or positive infinity. As x is going to negative infinity or positive infinity, what's happening to the function? Is it going to positive and negative infinity itself? Is it going to an asymptote? Something like that. So we had a procedure that you probably learned different ways of doing this. Like you learned that if the function is bottom heavy, the degree of the denominator is bigger, then that means that you're going to have a horizontal asymptote at 0. You learn that if the degrees are equal, then you look at the coefficients of the highest degree variable, and if the degree of the numerator is higher than the degree of the denominator, then you're going to be going to either positive or negative infinity. Okay, and that's all well and good, but for what we need to do in calculus, we need to be a little bit more precise, and we're going to actually deal with the limits. Okay, so here's the technique, and it's actually written out right here fairly clearly. Is that for each function below, you can see that each one of these limits is asking us to find a limit at infinity, and these are all positive infinity. We'll talk about negative infinity in a second. What we're going to do is divide every term in both the numerator and the denominator by the highest power of x that appears in the denominator, and then evaluate the limit. So we're not changing anything. We're not doing anything to the function. We're basically just going to divide numerator and denominator by whatever the highest power is. So if we look at this function, we've got x plus 2 over x squared plus 5x plus 6. We're going to say, okay, well, what's the highest power in the denominator? And it's 2. So what we're going to do is divide by x squared. And actually, I'm going to write it as multiplying by 1 over x squared over 1 over x squared. Okay, that's the same thing as it says here. It says divide every term by x squared. So that's what we're going to do. So we end up with the limit. Now, I'm not changing anything. I'm just multiplying by 1, right, in the form 1 over x squared over 1 over x squared. Where does that take me? Okay, x infinity. Okay, x times 1 over x squared is 1 over x. 2 over x squared is 2 over x squared. X squared over x squared is 1. 5 over x squared, 5x over x squared is just 5 over x. And 6 times 1 over x squared is 6 over x squared. Now I can do my substitution, and I'm going to do it in a kind of a funny way. I mean, I'm going to substitute. I'm not really substituting because you can't substitute infinity. It's not a real number. But what do you get? Okay, well, you get 1 over infinity. Well, actually, I'm just going to do it like this. If you put infinity here, 1 over infinity, 1 over an infinitely large number. This is a key thing. If this doesn't make sense, come talk to me. That's 0. If you take 1 or any number, really, and divide it into infinitely many pieces, you're going to end up with pieces that are really, really small. Infinitely small or 0. So 1 over x, 1 over infinity is going to be 0. 2 over infinity is also going to be 0. Squaring infinity is just going to make it bigger. So in the denominator, we end up with 1. 5 over x, so 5 over infinity, so that's going to be another 0. And then 6 over infinity squared is going to be another 0. So what do we end up with? 0 over 1, which is equal to 0. Okay, so now what do we do? I mean, it seems like we did something that maybe is not that interesting. We already knew that this end behavior of this function is 0, but what we did is we used limits. Use the limit notation, and now we can prove more with it to show that this limit is equal to 0. And the technique, again, was multiplying by 1 over x to the highest power in the denominator. Let's try the next one. Okay, highest power in the denominator here is x squared. So we'll multiply by 1 over x squared over 1 over x squared. All right, well, what do I get here? I've got a limit as x goes to infinity, 2x squared over x squared, so that's just going to give me 2. 7x over x squared is going to give me 7 over x. 6 over x squared is just 6 over x squared. X squared times 1 over x squared is 1. 5 over x, 6 over x squared. Okay, now I can evaluate the limit. All right, I'm going to have 2. Well, that's just 2. X goes to infinity, 7 over x, that's going to be 0 again. As x goes to infinity, 6 over x squared is also going to be 0. In the denominator, I've got 1. 5 over infinity, that's going to be 0. Limit as x goes to infinity of 6 over x squared is also going to be 0. Okay, so what if I got 2 over 1 or 2? Now, this is the same thing we got using our coefficient rule that you learned in Algebra 2 or whatever, but now, again, we're evaluating the limits, so we have a sense of like how this makes sense in terms of limits. Let's look at the last one. We said we always divide by every term by the highest x in the highest power to x in the denominator, so in that case that's x. Even though I've got x squared up here, I'm going to multiply by 1 over x because that's the highest power in the denominator. So 1 over x, 1 over x. Okay, what do I get? Well, x squared over x is just x. X squared over x is just x. 3x over x is 3, and then I get 2 over x. Denominator, I get 1 minus 1 over x. Okay, now I'm going to do my infinity thing. Okay, well, if I put infinity in here, it's not in the denominator or anything, I just get infinity. Okay, we'll see what happens with that. 3 plus 2 over x is going to be 0. That's as x goes to infinity. I got 1 minus 1 over infinity. That's going to be 0. So I've got infinity plus 3 divided by 1. Well, infinity plus 3 is just infinity. And infinity divided by 1 is also just infinity. So this is infinity. Does that make sense? Well, yeah, look at our graph. If we look at our graph, as x goes towards infinity, this function is going out in this direction, up towards infinity. And also just using our sort of Algebra 2 pre-calc rules, the degree of the numerator is greater than the degree of the denominator, which means that I'm going towards infinity or negative infinity. All right, so that's the technique. Let's keep trying and let's keep using that. And on the next page, these examples involve the limit as x goes to negative infinity. But we're going to do the same thing. Okay, highest power is x squared. So I'm going to go 1 over x squared, 1 over x squared. I end up with the limit as x approaches negative infinity. We'll see how much difference this makes. But let's just try our technique, see what happens. Okay, 2x squared divided by x squared is just 2. 7x divided by x squared is just 7 over x. And I end up with 6 over x squared again. The denominator, I've got x squared over x squared is 1. 5x over x squared is 5 over x. And then 6 over x squared. So what do I get? Well, it looks like I get 2 plus, okay, as x goes to negative infinity, 7 over negative infinity, that's going to still be 0. So it doesn't look like it's making any difference if this is negative infinity. And 6 divided by negative infinity, that's also just going to be 0. I mean, 0 is 0. It doesn't matter if it's positive or negative. I mean, there's no such thing. Right. You know what I'm talking about. Okay. Blah, blah, blah. 2 plus 0 over 1 plus 0 plus 0. Oh, it looks like exactly the same thing as we had before. Which is good, because that's what we should get. If we look at this function, as I go towards negative infinity, this function is going towards 2. As I go towards positive infinity, it's going towards 2. So we should be getting the same thing, negative and positive. Let's look at this one. Okay. This is our slant asymptote problem that we did before. We saw that as x went to positive infinity, it was going towards positive infinity. Let's see what happens. We do our same technique, but with x going to negative infinity. So we'll multiply by 1 over x over 1 over x. We get the limit as x goes to negative infinity. We get, x plus 3x over x is going to be 3, 2 over x, over 1 minus 1 over x. All right, now we can do our substitution. But now look what happens. If I evaluate this limit over here, my new limit, if I put negative infinity in for x, well, I get negative infinity. I get a very large negative number. Plus 3, plus 0 still, right? That doesn't make any difference. 0 is just 0. 1 minus 0. Okay. If I take a negative infinity, and I add 3, I've still got negative infinity. Divide by 1, still got negative infinity. So here, I get negative infinity. So just using the, I didn't use any different technique. Same technique that I used in the first case, when I was going to positive infinity. I use here, going to negative infinity. But I get negative infinity. And that's good, right? Because if we look over the graph, that's where I'm ending up. Okay. So, what did we just see? Well, based on what we've just seen and what we know graphically about the functions above, let's just scratch out that. Does approaching negative infinity make a difference in the result of our limits? And the answer is only if we have a slant asymptote. All right. This case, where we have the slant asymptote, it doesn't matter. It matters if we're going to positive or negative infinity. But if we're just going to here and here, where we have a horizontal asymptote, it doesn't matter whether we're going to the positive side or the negative side. At least that's what it looks like so far. But we're going to look at another case where it might be a little bit weirder in just a second. Go on to the next page. Graphically, a limit at infinity can yield. We need to know what the justification of the horizontal asymptote using limits. Okay. F of x has a, and I'm just going to write HA because that's already taken a long time. It has a horizontal asymptote if the limit as x approaches infinity of h of x equals c, or the limit as x approaches negative infinity of, f of x, I call this f of x, I should call it f of x, equals c, where c is a real number, right? Not infinity or something like that. All right. So for the function below, find the horizontal asymptote if it exists. Justify your answer using a limit. Okay. So we'll do our little trick. We'll do 1 over x squared over 1 over x squared, because x squared is my highest power. And I end up with 5 over x squared minus 2 over x minus 2 over 3 plus 2 over x minus 3 over x squared. And if I take the limit as x approaches infinity of 5 over x squared minus 2 over x minus 2 over 3 plus 2 over x minus 3 over x squared, I get 0 minus 0 minus 2 over 3 plus 0 plus 0, which gives me negative 2/3. And that tells me that I have a horizontal asymptote at negative 2/3. I'm going to go back, I'm going to stop here, and then I'm going to pick up the rest of the notes in the next video.